I've run out of board space, so I've had to erase the board and start over here again. And so you should have all of this in front of you. There's the full problem is worked out for you, so I'm hoping you can follow along here. Now, the next set of statistics that we calculate now, this measures the risk and return of the two assets if they were kind of mixed together in the same portfolio. And so this shows you the interrelationship between the asset I, the security I, and the return of the market. Now, the first statistic of this sort that we're going to calculate now, this is called the covariance. And covariance is the mean of the product of the deviations. So we're going to calculate a weighted average mean. We're going to multiply the deviations together, that's the product, and then we're going to multiply each of those products times its probability of occurrence. Now, covariance. Covariance takes on any value between negative infinity and positive infinity. Again, fairly wide range here. And most often people don't like to use covariance because it doesn't have any boundaries. It's you don't really have a sense of whether it's a high positive or a low negative or anything in between, really. But the first statistic we calculate, though, is the covariance. What you can say about covariance is the greater the positive covariance, the greater the tendency of the two sets of numbers to be on the same side of their mean at the same time. They could both be on the upside of their mean, positive times a positive is a positive, or they could both be on the downside of their mean, a negative times a negative is also a positive. So if it's a positive covariance, what you can say now is that the two sets of numbers tend to be on the same side of their mean at the same time. If it was a negative covariance, then what you would say is that the two sets of numbers tend to be on the opposite sides of their means at the same time. If one's is above its mean, it's got a positive deviation, and the other one's below the mean, it's got a negative deviation, a positive times a negative is a negative. So the greater the negative covariance now, the greater the tendency of the two sets of numbers to be on the opposite sides of their means at the same time. But this is the covariance statistic. Now, what you can see here is as you see up at the top now, this is the deviations for the security multiplied by the deviations of the market. And then we multiply those deviations multiplied together by their probability of occurrence. So if you'll look at the problem now, you see that the deviations for the security was a negative 9.2, when the deviations for the market was a negative 2. Negative 9.2 times a negative 2 multiplied by their probability of occurrence, 0.20, gave us 3.68. And note, they were both on the downside of their mean. These are both negative deviations. But a negative times a negative now gives you a positive number. The second observation, the deviation for the security was 1.80. For the market, a negative 3. They're on the opposite sides of mean. That would be a negative number. Multiply that by 0.30, you get a negative 1.62. So this negative meaning what? They were on the opposite sides of their means at the same time. One was above the mean, one was below the mean at that point in time. The third observation, the deviation for the security was 4.8. For the market, it was 6. Positive numbers multiplied by 0.40, you get a positive 11.52. And the last one, the last sets of observations, these were both negative deviations. A negative times a negative is a positive. Negative 6.2 times negative 11 multiplied by 0.1 gave us a positive 6.82. These are the products. Sum that, you get 20.40. And that's the covariance between the stock and the market. And again, a positive covariance indicates that the tendency is for these two sets of numbers to be on the same side of their mean at the same time. Now, because this takes on has no boundaries to it, we normalize the covariance term. Normalization typically means you're putting boundaries on the value the statistic can take on. A normalized covariance term, you'll recall, is a correlation coefficient. And the correlation coefficient is defined as the covariance, in this case between the stock and the market, divided by the product of the standard deviations. So if you take this covariance divided by the product of the two standard deviations, you find a correlation coefficient of a positive 0.6694. Now, correlation coefficients can only take on values between -1 and +1. In this case, a positive 0.67, this is a fairly high positive correlation. In a little while, we're going to figure out the formula that explains the returns of the security. And when we do that, we want to know how the model works. And to get an indication of that now, we calculate what's called the coefficient of determination, often referred to as R squared. R squared, the coefficient of determination, is simply the correlation coefficient, the little r squared. And so if you take 0.6694, square it, you get 0.4481. Now, R squared can only take on a value between 0 and 1. 0 would mean that the model that we've come up with explains nothing. +1 would mean that it explains everything. Ours is kind of somewhere in between there somewhere, 0.4481 or 44.81%. Roughly 45% of the variation in the security return is explained by the variation of the market. Something explains the other 55%, but we don't know what that is. The beta statistic, this is the slope of a characteristic line in investments, but beta is defined as the covariance between the stock and the market divided by the variance of the market. And in this case, the covariance was 20.40, and you divided that by the variance of the market, we got a positive 0.68. Again, this was the beta of the security.